How does a structure hailed as the ultimate masterpiece of evolution suddenly buckle and collapse under its own weight? It begins with a silent, invisible failure, a microscopic shift in alignment that triggers a total structural breakdown. Look at this engineering model. We've used industrial-grade corrugated cardboard, meticulously layered to simulate the exact density and load-bearing capacity of human bone. But watch what happens as we apply a standard vertical load. The failure is instantaneous. The lumbar region, specifically the L4 and L5 segments, doesn't just yield, it shatters. The internal fibers buckle, the structural integrity vanishes, and the entire column folds into a heap of useless material. But how is a biological pillar capable of supporting a human being for decades, only to fail so spectacularly at the slightest mechanical stress? The answer lies in a fundamental design flaw that would get any modern engineer fired. The secret isn't a lack of material strength. It's a catastrophic oversight in the blueprints of human evolution. We were never supposed to stand like this. For millions of years, the spine functioned as a horizontal suspension bridge, perfectly balanced to distribute weight across 4 points of contact. Then, everything changed. Evolution didn't give us a ground-up redesign. Instead, it delivered a desperate, high-stakes technical patch. We forced a horizontal beam to act as a vertical, load-bearing pillar. It was a biomechanical workaround that left our lower back as the ground zero of structural failure, the tip of the spear for every ache and rupture you've ever felt. It is a brutal, relentless confrontation between biology and gravity. This brings us to the ultimate question. How do we physically survive in a body that is, quite literally, a structural engineering disaster? The high-stakes history of human movement is about to witness a massive escalation. Think of the human spine not as a biological miracle, but as a vertical crane, a 25-foot structural assembly forced into a high-stakes environment it was never rated for. In a standard engineering blueprint, a crane is designed with a wide, stable base and a counterweight system to offset the load. But in the human body, we have a single, narrow pillar of 33 stacked bone segments held together by nothing but biological cables and pressurized gel pads. This brings us to the epicenter of the conflict, the lumbar region, specifically the L4 and L5 vertebrae. This is the ground zero of structural failure. When you are standing perfectly upright, the axial load on your L4-L5 discs is relatively controlled, roughly 500 newtons of force for an average adult. In engineering terms, the system is within its safety margin. But the moment you lean forward, the physics shift violently. Because the spine acts as a lever, leaning at a mere 20-degree angle increases the load on those lower discs to over 5,500 newtons. That is 3 times the weight of your entire upper body concentrated on a surface area no larger than a silver dollar. As the angle increases, the moment arm lengthens and the mechanical advantage shifts in favor of gravity. By the time you've reached over to pick up a simple box, the force slamming into your lower back can exceed 5,000 newtons. That is the equivalent of a small car being dropped directly onto your structural core. But the collapse doesn't happen in an instant. Just like a high-seas confrontation, the system executes a highly calculated strategy, an escalation of warnings. Your nervous system is the central command, issuing repeated orders for the vessel to change course. It starts with a level 1 warning, muscle tightness. This is the body's way of saying attention lower back, vacate the current position. You are entering a high-stress zone. Most of us ignore this initial directive. We stay seated. We keep leaning. We maintain the structural blockade against our own recovery. When the warning is foot low, the system escalates to level 2, persistent inflammation. The chemical sensors in your soft tissue begin to fire, creating an internal heat that signals structural fatigue. Your brain hails the region over the neural radio with a chillingly specific directive. Lumbar sector, cut your engines, reduce load immediately or face disabling fire. We respond by taking an aspirin, the equivalent of cutting the radio wires so we don't have to hear the siren. We continue to steam ahead at full speed into the storm. Now we enter the countdown to total structural failure. Gravity is a relentless enemy. It does not sleep, it does not negotiate, and it never runs out of ammunition. It is a 24/7 kinetic operation against your discs. While you sleep, the discs attempt to rehydrate, to refuel for the next day's combat. But the moment you stand up, the blockade is back in place. The pressure returns. Consider the disabling fire of the spine, disc herniation. This is not just a leak, it is a tactical strike on your mobility. Inside each disc is the nucleus pulposus, a pressurized, jelly-like core. Around it is the annulus fibrosus, a series of tough concentric rings of biocarton-like fiber. As the years of running the blockade add up, these rings begin to fray and crack. The structural integrity of the wall is compromised. Then comes the final escalation. You make a routine move, teeing a shoe, reaching for a coffee, and the countdown hits 0. Under the overwhelming shear force of a misaligned lift, the outer wall of the disc ruptures. The pressurized internal gel slams through the breach. This is a surgical strike on the most sensitive hardware in the human body, the nerve roots. The result is an instant internal fire, a blinding electrical surge that travels down the leg, mimicking the path of a missile strike along the sciatic nerve. The vessel is now dead in the water. Propulsion system is offline. The manual loading of your daily tasks has been forcefully terminated by a mechanical breakdown. But why is this system so prone to such a catastrophic kill shot? To understand the vulnerability of the human crane, we have to look deeper into the individual components. We have to strip away the skin and muscle to see the specialized armament of the vertebrae and the automated suspension system that is supposed to protect them. The secret to our survival and our inevitable breakdown lies in the 4 distinct parts of the spinal column's ammunition handling system. Watch how it operates under pressure. This brings us to the tactical breakdown of the most sophisticated and most fragile engineering project in natural history. But how does this biological crane actually withstand the relentless bombardment of gravity? To understand the failure, we must first appreciate the engineering. This sophisticated biological assembly can be compartmentalized into 4 distinct functional parts, each serving a critical role in the structural integrity of your core. Starting at the base of the operation is the ammunition shuttle, or what clinicians call the vertebral bodies. Think of these as the heavy-duty loading blocks of the system. In our engineering model, we've represented these using high-density, double-walled corrugated cardboard. In a healthy human, these segments are stacked in a precise, vertical column designed to shuttle the weight of your skull, rib cage, and organs directly into the pelvic cradle. But look closer at the internal architecture. The secret lies within the bone itself. While the outer shell is a hard, cortical casing, the interior is a lattice of spongy, trabecular bone. This design is a masterclass in lightweight engineering, providing maximum strength with minimum mass. However, this is also where the system is most vulnerable. Under a sudden high-velocity axial load, like a hard fall or a heavy lift with a rounded back, this internal lattice can buckle. This is a compression fracture. The shuttle doesn't just crack. It loses height, permanently altering the alignment of the entire system and triggering a cascade of mechanical errors up and down the line. Just above the vertebrae, we encounter the automated handling system, the intervertebral discs. These are the hydraulic shock absorbers of the human machine. To visualize this, we've integrated a specialized composite, layers of tough, crosshatched cardboard surrounding a pressurized core of soft, translucent vellum. This system is a miracle of fluid dynamics. The outer rings, the annulus fibrosus, are designed to handle massive tension, while the inner jelly, the nucleus pulposus, handles the compression. When you move, the fluid shifts, distributing the force evenly across the bone. But what happens when the pressure becomes asymmetrical? If the load is concentrated on one edge, common in a sedentary, slouched posture, the internal fluid is forced against the back wall. Under enough pressure, the vellum-like outer shell begins to fray. The automated handling system begins to leak. This is the structural equivalent of a hydraulic failure in a naval gun. Once the fluid is compromised, the bone-on-bone friction begins, and the system loses its ability to absorb the recoil of daily movement. Progressing forward to the rear of the column, the next component is the loader drum, known as the facet joints. These are the mechanical stabilizers that guide every twist and turn of your torso. Imagine them as a series of interlocking gears that allow for smooth rotation while preventing the column from sliding out of its designated track. When you lean back or rotate, these joints engage to lock the structure into a stable firing position. But here is the critical flaw. The loader drum is the point of greatest weakness during torsion. The human spine is exceptionally strong at handling vertical pressure, but it is dangerously fragile when dealing with a twist and lift maneuver. When the drum is forced to rotate beyond its rated capacity, the cartilage wears thin and the bone begins to grind. The result is a total mechanical lock. The system becomes unresponsive, freezing your movement in a desperate attempt to prevent a complete structural disconnect. Positioned around the entire setup is the gun shield, a complex network of ligaments and core muscles. This is the frontline defense, providing essential protection and stability to the internal hardware. In our tactical papercraft model, these are the high-tension fibers that keep the cardboard segments from collapsing into each other. These muscles, the multifidus and the transversus abdominis, are supposed to engage milliseconds before you move, preloading the system for the incoming force. They are the software that runs the hardware. But in the modern world, this software is often glitchy. Long hours of sitting offline in a chair cause these muscles to atrophy. The shield becomes thin. The stability vanishes. When an unexpected load hits, a stumble, a sneeze, a sudden reach, the shield fails to activate. The force bypasses the protection and slams directly into the delicate internal components. Together, these four integral components form a seamlessly integrated system that handles thousands of newtons of force every single day. But what happens when the hardware is under constant, low-grade siege? This is where the statistics become truly staggering. When the automated handling system fails and a disc herniates, it doesn't just cause a dull ache. It locks onto the nerve roots with surgical precision. When this happens, your nervous system begins to spit out 4,500 pain impulses per minute. To put that in perspective, that is the exact firing rate of a Phalanx CI-dub Gatling gun. Your brain is being bombarded by a relentless stream of high-velocity signals, effectively stripping your mental bandwidth bare and leaving you in a state of total structural alarm. The shell case of your mobility is ejected with every bad movement, but unlike a naval destroyer, you don't have an endless magazine of replacement parts. Every micro tear in the disc and every grind in the facet joint is a permanent loss of structural ammunition. But what if the threat isn't a sudden, heavy load? What if you are dealing with a slow-motion blockade, a silent threat that has been lurking beneath the surface of your lifestyle for decades? While we focus on the spectacular failures, the real danger is the everyday attrition of the modern environment. We have taken a high-performance kinetic machine and forced it into a state of permanent, stationary lockdown. This is the biomechanical equivalent of a naval fleet trapped in a harbor while the enemy swarms the gates. The transition from a structural masterpiece to a technical disaster is almost complete. But there is a second layer of defense. What if you could execute a precision tactical drop to retake control of the bridge? What if you could reinforce the shield and repair the automated handling system before the final collapse? In the next phase of our operation, we delve into the strategic countermeasures. We are going to look at how to break the blockade of a sedentary life and raise the flag of structural resilience once again. The siege of the lower back is about to face an overwhelming counter-assault. This is the climax of the human structural war. But what if the most dangerous threat isn't a sudden impact? In this scenario, the enemy isn't an external force, it's the office chair. This is a silent, slow-motion blockade, a clandestine operation that has been stripping your mobility bare for decades. It is a strategic siege on your natural sagittal balance, a habit identified by your body's own intelligence as part of the sedentary fleet, the network of industrial habits used to bypass your biological sanctions. This is where the geopolitical chess game of your health escalates into a kinetic operation. When the habits refuse to stop, you must dispatch your elite forces. We don't neutralize the threat with torpedoes, we use overwhelming biomechanics. These are the special operations teams of targeted movement, fast roping from the hovering helicopters of focus rehabilitation directly onto the deck of your chronic stiffness. Leading the surface chase is the legendary cutter of your own core strength, stalking the structural breakdown through the brutal ocean swells of aging. Within minutes, these tactical drills secure the bridge of your pelvis, cut the engines of muscle atrophy, and raise the flag of resilience. This is when your mobility is yours again, and the blockade is officially enforced. Look at our tactical model one last time. We have reinforced the collapsing cardboard vertebrae with high-tension nylon cord and industrial-grade vellum splints. It is no longer a buckling stack of paper. It is a reinforced biomechanical fortress. Even when we slam this massive load onto the top, the column refuses to yield. It stands dead in its tracks, intact and unshakable. The human spine may be a structural engineering disaster, a desperate technical patch on a horizontal design, but it is the most resilient disaster ever built. It is a masterpiece of survival. But what tactics is your own body following right now? If you are looking to upgrade your structural defense, you need to check your own front line. Think of your posture as your first layer of defense. It scans for threats, alerting you to dangerous microstresses before they trigger a hard kill on your movement. Go ahead, scan your settings right now. Correct the alignment. Secure the vessel. The high seas of your life are about to witness a massive escalation, and you need your flagship to be ready for the hunt.